Recently, our client John met his banker to discuss plans for a clean energy building. What he found was a shared passion for building something more. Momentum for change. First Horizon Bank. Let's find a way. Go to firsthorizon.com/John.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thanks for joining us. This is the Space Nuts podcast. My name's Andrew Dunkley, your host, and joining me, as always, Professor Fred Watson, Astronomer-at-Large. Hello, Fred.
Hello.
How are you, sir?
doing, Andrew?
I'm well.
I'm well, thank you. Yeah, we're both well.
Hopefully.
Which is good in this day and age. Yes. Yeah. I was tested on Friday, so I know that as of Friday I was okay.
Yeah, we're talking about the new COVID cluster which broke out in the Northern Beaches area of Sydney. At last count, there were 90 cases, and I think from what I've heard, they've managed to haul it in. But I'm sort of preceding my comments because the state premier hasn't made her latest statement yet. So we'll have to wait and see on that. And by the time this podcast is out, we'll know where it stands. But it looks like they got it early and they've really slowed down the potential for it to get out and about, which is great news. But it scotched our plans. We were going to Sydney to see our boys next week. That's not going to happen. So unfortunate, but you've got to be safe, and we'll catch up with them again at some other stage. Now, Fred, we have got an interesting episode this week, a very interesting episode, because you don't know what's happening. You've you've been left out in the dark. Yeah, which is part of your job. Let's face it, that's part of your job, to be left out in the dark. But we are doing questions without notice today. Questions without notice. So we've got a bunch of audio questions here from a whole array of people all around the world who have sent them in very kindly, and we appreciate that. And we're just going to play them and see how Fred goes. So totally unrehearsed, totally without notice. So let's just get straight into it. Oh, no, before we do, Fred, I must say, I tried to look at the Great Conjunction the other night, and I was very disappointed because it rained. I mean, it poured here. The cloud was thick. You couldn't see past it, and we missed the event. Now, I did have a look a couple of nights earlier, and I did take a photo, but unfortunately my little camera just didn't have the oomph to get a real good close-up picture of Saturn and Jupiter. But apparently you got a look at it last night, did you?
Yeah, I did, yeah. There was a lovely occasion last week when the Moon and Jupiter and Saturn were pretty close together in the sky, and I got some nice pictures of that. This was before the conjunction, though. This was on Thursday.
Okay.
Week. So the conjunction day, yes, the whole of New South Wales was washed out by cloud and rain, and it poured down here in Sydney. There was no chance of seeing anything, and I tweeted my disappointment. Then last night, though, knowing that the planets were still pretty close together, I think still less than 2 degrees apart, I had a look again. There was, at sunset, there was the most beautiful sheet of clouds being lit from the underneath by the sun. And that was a disappointment because I thought, well, we're not going to see anything through that. But it was so stunning. I tweeted a picture of it because it really looked great. But then at about 9:30, when I knew that Jupiter and Saturn were about to set in the western sky, I had a look out again, and they had gone below the cloud deck. So we could see them.
Wow.
We could see them. Very low down in the sky, actually getting mixed up with the trees that surround our property. But through binoculars, it was just stunning, with Jupiter directly above Saturn, very, very close by. I could just about make out a hint of the moons of Jupiter. It was very poor conditions because they were so low on the horizon, but and it was only 7x50 binocular, but still we got them, and it was just brilliant to see. So the conjunction itself must have been truly spectacular, because 24 hours later it was still looking pretty damn good. So I was very glad to get that.
I saw some absolutely brilliant photographs on Instagram and Twitter and a few other places. People with really good equipment, obviously, and good telescopic equipment that were able to get such really vivid pictures of those two planets close up. And, I congratulate them for that. They did a fabulous job.
Indeed, that's right. So you're quite right that with a telescope or a telephoto lens, the two planets would be resolved as planets and you'd see the details on them, but within the same field of view. It's just fantastic.
It is, yeah. Terrific stuff. And which you just reminded me, I've got another camera that I could have used, which has got a super duper lens, and I didn't think of getting it out and dusting it off. I should have done that. Not too late. I might have a crack tonight.
Yeah, have a look tonight because it's still worthwhile. Hopefully the sky will be clear.
Fingers crossed. Okay, let's go to our first audio question, and a question without notice for you, Fred. This one comes from Kate. Now, I've got to take these off so that we can pick up the audio. So bear with us. This is also, technologically advanced. Here we go.
Hi, my name is Kate. I heard the episode on the 3rd of December, and the first question a guy asked about whether the universe, supposed that the universe was round. And it made me question, because I was reading something about that this morning, are there any theories about what the universe, whatever shape it is, what it's suspended in? It's a silly question, I guess, but I'm just curious. What do scientists believe the universe, or universes if they're more than one, what does it exist in? If you could have any thoughts on that, that would be great. Thanks.
Okay, thank you, Kate. Kate's from Australia, mate, I'm sure. What is the universe suspended in?
Yeah, it is a brilliant question. And it's one of these questions that there really isn't an answer to. We can theorize what the possibilities might be, but there is no certainty at the moment. The main issue, I guess, is how you define universe, because the formal definition of a universe is, it's the universe, because it is everything you can ever detect or see or measure. In other words, the word itself precludes there being anything beyond it. And that actually is the way most astrophysicists tend to look at the universe, as a single entity, which is probably without a boundary, although it may not be infinite. And what I mean by that is, if you think of the Earth is certainly not infinite, but it doesn't have the surface of the Earth doesn't have any boundaries in terms of, your physical ability to move around it. Clearly there's ocean and things of that sort, but the surface of the Earth is boundless, but the actual Earth itself is not infinite. It's a finite size. So the universe you can think of it as a kind of three-dimensional analog of that curved surface of the Earth. And that is really the only way we can get our heads around it. It may actually be infinite. There may be no limits to it. There are limits to how far we can see. The cosmic microwave background shuts a curtain down at about a look-back time of 13.8 billion years. But it may be, it may be that the universe doesn't have to exist in anything. It is everything. And its beginning was the beginning of space and the beginning of time, whatever that event was. Now, some scientists think that's a bit unsatisfactory.
Of course.
So, and they wonder about other universes. I mean, Martin Rees, the Astronomer Royal, he was one of the early proponents of the idea of a multiverse, multiple universes. And then you say, okay, well, where are they? So, is there, what does the universe sit in? Exactly as Kate has said. The usual thinking on that is a higher dimensional space. And so that gets you heavily into mathematics, because in mathematics you can have as many dimensions as you want, and geometry lets you do that. And in fact, most of the thinking on this is very geometrically orientated in its mathematical formulation. So if you can imagine, perhaps we know that our universe has the 3 dimensions of space: up, down, side to side, backwards and forwards, and 1 dimension of time. If you had a 5th dimension, for example, which was hidden from us for some reason, could other universes sit within that dimension? And actually, one of the thinking, it's something one of the thought processes along these lines is something called M theory, and the M stands for whatever you like. Actually, it could be membrane is probably the usual word. Yep. That universes are imprinted on something that is like a 2-dimensional membrane, but it's in 3 dimensions, and these membranes float around in a higher dimensional space. That's perhaps the most easy to get your head around view of what the universe might be like. Now, how do we detect what's in the it's actually called, what's it called? It's got a name. It's called The Void by Doctor Who. Oh. But in astrophysics, we've got another name, which is eluding me at the moment. That's what you get for questions without notice. Yes. It'll come to me in a minute. Anyway, this high dimensional space, how do you detect it? So maybe, and some people have looked at the possibility of seeing evidence of other universes through the imprint of patterns on the cosmic microwave background radiation, this basically hiss all around the sky in the microwave region of the spectrum that is the flash of the Big Bang. That's got these hot and cold spots imprinted on it. And by looking at patterns in those, we can say a lot about the Big Bang. But some scientists have said maybe we can say a lot about other universes as well. Yeah.
There's multi-universes in one of my books.
Oh, of course. I would expect nothing less from you, Andrew.
But when you said that it might be infinite, which means it never ends, therefore it can't be suspended in anything. How do you get your head around that? I mean,
well, you don't really. It is a puzzle. It's something. It's so counterintuitive to our thinking because we're used to a 3-dimensional world with a dimension of time
with limits.
We can't do anything about. With limits. That's right. Yeah. A good question.
Not a silly question at all, Kate. Wonderful question, because I suppose that's where astronomy is at its best, because they're trying to answer these impossible questions or improbable questions, the things that we just try to understand that are beyond our comprehension. And I suppose that's the big challenge in astronomy, Fred, to come up with answers.
Indeed. I think I've remembered what we call the space between universes in astrophysics, but I'm just checking that I'm not making this up.
I was talking to a guy the other day, and it was actually an on-air, live-to-air interview, and I asked him a question, and he just couldn't think of a certain name or word. And he said to me, when this is happening, I say my brain is buffering. So I thought that was brilliant.
Very nice.
So
Very nice.
Let's spread that one around. Yeah. If you can't think of someone's name in a conversation.
It's actually, I've remembered correctly, it's called the bulk.
The bulk.
The bulk. And if you look that up and define it, it tells you it's the higher dimensional space between universes or membranes.
Very good. All right. Thank you, Kate.
Now, Andrew, for some reason, I've lost your voice altogether. Oh. I can't hear anything you're saying, and I'm not sure why.
Okay. This is odd.
Hang on. Hang on. Let me try again.
Okay. Can you hear me now?
Yeah, for some reason, probably because I went to another web page, it muted your mic.
All right. Am I unmuted now?
You're very unmuted.
All right.
Definitely.
Well, please don't teach my wife how to mute me, because
she knows already, doesn't she?
It's hard to get a word in now anyway. So, all right. Let us continue. This is another question without notice from Jeremy, and he's in Utah. So here we go.
Oh, great.
Hello, Fred and Andrew. My name is Jeremy from Utah. I have a question about your favorite subject, black holes. And the question I have is one I haven't heard, though, before. And it is whether the event horizon of a black hole can have ripples on the surface, if there is such a thing. Anyway, I love your show, and I will have a listen.
Yeah, well, I'm glad that'll make one of us. Thanks, Jeremy. Black hole event horizon, does it have ripples?
What a great question. And I think, so once again, this is, coming from what I know about black holes, which is mostly gleaned from other scientists I've spoken to and things of that sort. So the event horizon is, in a sense, an illusory aspect. It is the point at which the light from the black hole cannot escape from, beyond. So you can't see anything beyond the event horizon. And I think because of that, and because the black hole itself is a single point by definition, it's defined to be a dimensionless point in space, that means that the event horizon must be a perfect sphere. It must take, basically it's got to be at the same distance everywhere from that single point. So my guess is that the answer to that is no. But it is a great question. And next time I'm talking to one of my black hole specialist colleagues, who sadly are mostly unavailable at the moment because of the COVID lockdown here in the northern beaches. Next time I'm doing that, though, I will ask that question. It's a great question, but I think the answer is no. No ripples.
No ripples. So it would be a perfect sphere. Yeah.
Yes.
Which basically means that the term black hole is inaccurate.
Look, it's a term that is cobbled together. That's right. It's not a good name. It's one that was suggested in the 1960s, and it was
he's buffering again.
Physicist. I am buffering. That's right. John Wheeler, who coined it. I wrote about the naming actually in Cosmic Chronicles, or Exploding Stars and Invisible Planets, if you're reading.
As it's called overseas.
The USA. Yes, that's right. Yeah.
All right, Jeremy, thanks for the question. Simple answer, no, probably.
Probably.
But, we could do a sequel. Who knows? But thanks for the question. We are going to take a little break, but we've got a whole bunch more questions without notice for Fred soon on the Space Nuts podcast.
Roger, you're loud and clear here also.
Space Nuts.
This is the Space Nuts podcast. Andrew Dunkley here with, of course, the good Professor Fred Watson. And being our last program of the year, probably a good opportunity to send out some thank yous to our patrons, the people who've put a little bit of money in each month to support the podcast. You know who you are, and we are most grateful for your support of the idea that the audience brought to us. We didn't even know the concept existed, to be honest, but here we are. And thank you for all your support, whether it's through patreon.com or through Supercast or Acast, whatever it is. And of course, now we've got package deals. There's all sorts of ways you can support the podcast, even if you just want to make a one-off donation. Totally up to you and totally voluntary. We will never say you have to. But to those who have decided to get on board, thank you very much for doing that for us. Now, Fred, let's continue with our questions without notice. And this one comes from Andrew, who is in Victoria, but not Victoria, Australia, Victoria in British Columbia.
Hey, Andrew and Fred. This is Andrew here, longtime listener from Victoria, BC, Canada. I have a question for you about the orbits of spacecraft. I was reading up on the Dawn mission recently and how close it got to the Ceres dwarf planet. I noticed that apparently it got as close as around 30 kilometers above the surface. And my question for you is, hypothetically, how close could a spacecraft get to a celestial body? Would it hypothetically be possible for an astronaut standing on the surface of the moon to see a spacecraft, whiz past them at just a few meters above the ground? and the spacecraft to survive. Of course, if it was going fast enough, I'm sure this would be possible, but just based on the speeds they generally travel, how close could a spacecraft get to the surface of, either the moon or another celestial body that's, relatively large? Thanks for taking my question, and keep up the good work.
Thank you, Andrew. I suppose, Fred, it depends on the celestial body, doesn't it?
Well, it does, yes, of course. But that's a fantastic question. So, for example, if you consider the Earth, what stops you getting low to the surface is the atmosphere. So,
and the mountains. Yeah.
We'll do the mountains in a minute. It's the atmosphere that, because your orbital speed, the orbital speed of a spacecraft, the typical orbital height of about 200, 300 kilometers is nearly 8 kilometers per second. And it gets slower as the further away you go. So the nearer you get to the surface, the faster you've got to go to stay in orbit. But with the Earth, you've got the atmosphere, and clearly the atmospheric friction at that speed just burns you up, and there's no surviving that. But I think, the question is on the money, because there's not really, with a body that has no significant atmosphere, and the Moon and probably Ceres do have a gaseous envelope, but it is extremely rarefied. It's called an exosphere rather than an atmosphere. There's so little in it that it's almost not there, but it does have an atmosphere. And that, that could provide a limit as far as the Moon's concerned. But if it was a totally airless body with no atmosphere whatsoever, you're right. I think it would be the mountains that would be the limiting factor. They would decide how low you could get. Now, the reason why, with a body like Ceres, I think the question's correct that 30 kilometers was the minimum height. The same is true of Lunar Reconnaissance Orbiter. I think the minimum height of that spacecraft is 30 kilometers. And what you're doing there is choosing a height that lets you get some useful data from it. Because if you're too near the surface, you're not going to be able to get decent imagery of the surface, even though it's very near. The fact that it's whizzing by so fast makes it very difficult. And so that will be a compromise in terms of what useful information you want to get from the mission, but yet get the nearest that you can to the surface looking at. And we've seen marvelous images from Lunar Reconnaissance Orbiter, in particular of all the Apollo landing sites. So yes. I suspect there's no physical limit until you start hitting things on the surface. If you've got a completely airless world, there would be another consideration, and that is that most bodies in the solar system are not perfectly spherical. So, while you might be 100 meters above the surface at one point, you might be hitting the surface at another, usually the equator, where it's slightly flatter. So that's another consideration. But no, really interesting question again. And as I said, it's all a compromise. And
in answer to his question about what astronauts standing on the moon would see, that they would easily see a passing spacecraft, I imagine.
Yes, you would, yeah. Especially if it was close enough to be going at that really dramatic speed.
Well, it wouldn't be much, at speed, yeah. But even on Earth, you can see passing aircraft quite easily. You can see passing spacecraft at very high altitude, crossing the sky so very quickly. So at 30 meters, I reckon you'd probably see that. Most definitely.
I used to live near an RAF base in Scotland, and quite often we had jets almost at supersonic speed, less than a kilometre, probably less than 1,000 feet to use aeronautical measure. And they certainly lifted your hair, because I had hair in those days that could be lifted.
Well, that's funny, because I grew up not far from what is Williamtown RAAF base. And when I was growing up, the fighter bomber of the day was the Mirage, the French Dassault Mirage, and they quite often were very naughty and broke the sound barrier. They weren't allowed to, they weren't supposed to, but occasionally I'd be out in the backyard killing ants or playing cricket or something, and we'd go, you'd hear it, you'd feel it, not at the same time, but it was, and they quite often got into trouble for that. Yeah. All right, Andrew, thanks for your question. Let's move on to our next question. This comes from Spain, but I must confess, I can't catch the name. But maybe Fred will pick it up. But let's see how we go. This one, well, no, I'm not allowed to tell you. It's a question without notice. Here we go.
Hi, Andrew and Fred. This is Marcos Cremades from Spain. The other day, I heard one of your podcasts, and you talked about the precession of the rotation axis of the Earth. And Fred said that took 26 billion years. And I wonder how the hell can we know that time, okay? And just that. I love the show, enjoy pretty much all your comments, and I practice very much English with all that. Thank you very much. Bye-bye.
Thank you so much. Nice to hear from somebody in Spain. I didn't catch the name. Did you catch the name, Fred? It was, yeah.
Sadly, no.
But
it's very nice to hear. Very nice to hear.
Yeah. Now, I gather from the question he's wondering about how we know it took so long for the Earth to reach its orbital axis. I think that's the gist of it.
It's the precession of the Earth's axis. So the Earth is spinning, and if you think of a spinning top on a table, you can see it spinning, but the axis wanders around as well. And that's the phenomenon of precession, and the Earth does it. And it goes around once, not in 26 million years, but 26,000 years. It's a 26,000 year precession. I hope I didn't say 26 million. I doubt I did, because it's very much in here. 26,000 years. In fact, I can almost remember the last time it was around. So it's actually extremely easy to measure, because the result of that is a change in the apparent measured position of all objects in the sky. If you think of it, as the Earth rotates, we base our measuring system of where celestial objects are on the equator, the Earth's equator.
Right.
So the Earth's equator is basically wobbling around with this 26,000 year period. And so whenever when we specify the position of a celestial object, we have to specify what's called the equinox, and that's it's to cover precession. So most of the positions we use these days are corrected to the equinox of 1950.0, and that means where the precessional axis was in 1950, because it's moving all the time. With a 26,000 year period, it kind of, when you're measuring things with positions of less than an arc second, that actually moves quite quickly, and it's pretty easy to measure.
Okay.
It would be harder. It would be harder if it was 26 million years.
Yes.
That would be more difficult to do.
Yeah, I imagine.
26,000 years is easy. In fact, it's slightly, if I remember rightly, it's slightly less. I can't remember the exact number, but it's known to, probably a few months, the actual amount.
Mm. Well, we can fix that with a leap decade or something.
Yeah, leap decade would be all right.
Yeah. Let's do one backwards. We can all get younger. But thanks for the question, and certainly lovely to hear from somebody in Spain. Our next question, Fred, comes from a fellow. I think Russell has asked many questions of us. And I don't know if he's trying to be tricky by changing his name to Rusty, but I doubt it. That's probably his nickname. But he is in Donnybrook in Western Australia.
Fred and Andrew, g'day. It's Rusty Nuts from Donnybrook in WA. My question is about stellar abundances, and I'm wondering if there's been a study done on young galactic clusters on abundances of different spectral classes, and I'm wondering if that study would lend some insight into the makeup of globulars. Fred, you've told us a few times that globulars are made up of very old stars, but they can't have always been that way. And I'm wondering if a study of young galactic clusters will lend some insights into what might have been in the globulars and what could be there now in terms of what we can't see. We know we can see probably nearly all K-class stars, but I think the red dwarfs of anything so far away would be very difficult to see. White dwarfs, virtually impossible. And of course, we can't see the neutron stars or black holes that may be there.
Okay, I think the system cut him off because he had a lot to say. But Rusty, thanks for your question. Rusty nuts, probably better than space nuts. I'm not sure, but started with stellar abundances. So let's sort of go there first.
So Rusty should be an astrophysicist because that's all basic astrophysics. What he's talking about.
Wow.
Except when we use the term abundances, we're usually referring to the mix of chemical elements in the atmosphere of a star. And I think what Rusty's referring to is how many stars of different spectral classes, the categories into which we put stars, which are basically based on their temperature. But Rusty, you're absolutely right. Open clusters are probably the most studied objects in the galaxy because of what they can tell us. And it goes back to the earliest days of astrophysics. When people looked at open clusters, they realized that, first of all, they were probably seeing things which were all born at the same time, so they're the same age. And that also that they're all effectively at the same distance, so you don't have to worry about any distance considerations when you're looking at their brightnesses, and that's why these clusters have been such important bedrocks of the study of astrophysics. And I should just put the backstory here because we recognise two quite distinct types of star clusters in the world of astronomy. And these are, of course, on a much smaller scale than galaxies, which are hundreds of billions of stars. An open cluster, and it's sometimes called a galactic cluster because you see them mostly in the plane, the disk of the Milky Way. They typically have maybe 1,000 stars, 100 to 1,000 stars. The best known is the Pleiades, the Seven Sisters, the Hyades cluster, which is not very far away from the Pleiades in the sky. These are well-known objects. They're very, very pretty to look at through telescopes. They're certainly my favourite things with a small telescope because they kind of twinkle away in space there. But they are often still encased in some of the gas cloud that they were formed from, the gas and dust cloud. If you photograph the Hyades with a reasonably decent telescope, you'll see the blue light, which is dust scattering the light of the young stars. And that tells us that open clusters or galactic clusters, they're young. Their ages are measured in millions of years, whereas now globular clusters are entirely different. They're typically hundreds of thousands to 1 million stars. The bigger ones are around about 1 million. The two biggest ones in our neighbourhood, or the two most spectacular ones in the sky, are actually both in the southern hemisphere, Omega Centauri and 47 Tucani. So they're quite different objects. They're old, exactly as Rusty said, but they have a different origin, because we think now that they are the nuclei of dwarf galaxies that have been ripped up by the gravity of our own galaxy. In other words, they're remnants of galaxies that have been engorged into our own Milky Way. So all the outer stars have been stripped off by gravitational forces, and you're left with this tightly packed nucleus of stars, some of which we do know contain black holes. So they are a study in their own right, and we can't really make comparisons between open clusters and globular clusters because they have two different evolutionary paths. open clusters being new objects, relatively new in the galaxy, globular clusters being among the most ancient that we can find. Great suggestion, though.
Yeah, fascinating. Thank you, Rusty. Thanks for your question. Thanks for your support. I know you've sent us questions many times, and they're usually quite. Let me put this in a delicate, very, very. So I'm buffering. Detailed, very detailed.
And perceptive, if I may say.
Yes, very perceptive indeed. Thanks, Rusty. Appreciate it.
Yeah.
You're listening to the Space Nuts podcast. Andrew Dunkley here with Fred Watson.
Space Nuts.
This is the Space Nuts podcast, episode 234. Our last program for 2020. And again, thank you to everybody, particularly our sponsors. Already thank the patrons who've done a fabulous job for us this year, but our sponsors for getting behind the program and believing in it, because we started out with nothing, and what do you get when it's all over? You get nothing. And so we've had nothing to offer, and they've still supported us. So we're very thankful to our sponsors who have also put a little bit into the coffers of the Space Nuts podcast. And our social media supporters, the people who talk to each other on the Space Nuts podcast group on Facebook, and those that follow us on social media, whatever the platform, thank you to you too. Much appreciated. Now, Fred, we've got a few more questions to knock over before the end of the year, which doesn't give us very long. Comes from Damien, and I don't know where Damien's from, but let's hear what he's got to say.
Question about space-time and dark matter. When we calculate the mass of the sun and the planets, does Newton's laws of gravitation and Einstein's equation of space-time take into account dark matter? I guess not, since Newton didn't know about the dark stuff. So does that mean there isn't any dark matter in our solar system? Or it is included in the calculations? Then dark matter is 27% and normal matter is 5%. Is the sun, Earth, and us mostly dark matter? Thanks, guys, for a great show. Damien Huxley.
Thank you, Damien. Yeah, I guess Newton probably wouldn't have known about dark matter. He knew about a lot of things, but in working out what he worked out, he couldn't have catered for it, could he?
No, that's right. And there's a sense in which you don't need to. And that is because we believe, and the evidence points to this, that dark matter on the scale of the solar system is pretty uniform. It's not anything that would cluster near the sun. It's one of the unknowns about dark matter is what kind of particle it is. It's thought to be a heavy subatomic particle. There's a lot of research going on, Andrew, today about alternative theories as to what dark matter might be, because all the quests so far haven't really turned up what we thought it was, a subatomic particle that doesn't interact with normal matter. It doesn't interact with normal matter, so the sun and planets sit there unaffected by it. But the reason why I take it into account in orbital calculations is because of the scale. Dark matter is uniform on the scale of the solar system. It's a different matter, if I can put it that way, when you look at the scale of the galaxy, because the galaxy is clearly, it's obviously influenced by dark matter. And that's how we know dark matter is there, because galaxies don't behave the way that they should if all you can see is all that there is.
Yeah.
So that's the bottom line. It's all about the way that dark matter clumps. It clumps on the scales of galaxies, but doesn't clump on the scale of solar systems.
Okay. Wow. And I suppose he's prompted a thought in my mind. So we know it's there. We don't know exactly what it is. We don't know why it is. We don't know how it is. But is it like everywhere? I mean, I'm sitting in a not so palatial office at the moment. Am I surrounded by dark matter?
Yes, you are.
Oh.
And it's not interacting with you or with the radio signals, the sound. It's not interacting with anything. But you are in it, and I am too. at the ratio of about 5:1 to normal matter. Exactly.
Wow.
As Damien said. Yeah.
That's incredible. Yeah. And
it's a bit spooky, isn't it?
It is very spooky.
Andrew, yeah, that there's still a move afoot to try and get rid of it altogether. In other words,
remove it from our thinking.
Yes, because one of the first, so back in the 1980s, a physicist called Mordechai Milgrom, who's in Israel, he built a theory which is called MOND. And MOND is just short for Modified Newtonian Dynamics. And what it says is that at very, very low levels of acceleration, Newton's laws don't work, that the acceleration doesn't behave the way that we think it does. And you only get low levels of acceleration on scales of the galaxy. You don't get them, the levels of acceleration that our planets feel as they are orbiting the sun are far too high for the MOND theory to be interested in them. But when you get to very low accelerations, the suggestion is things are different. And that is why we see galaxies rotating in a different way. The problem that MOND has always had, and the reason why it's not universally accepted, although there are still researchers working on it, I know one of them personally, and he listens to this podcast. Peter, how are you doing? The reason why it's not really accepted is because it doesn't seem to work in other situations, galaxy clusters, and maybe in the overall evolution of the universe. But the research that's being done, it may be that we are opening up another new path to understanding what dark matter is. And actually, there is a third strand. There's another colleague of mine who is working on the idea that there is an unusual form of hydrogen, which we've ignored and neglected and not known about. But this hydrogen is actually what makes up the dark matter. Okay. I'm not too familiar with that theory, but that's something else that's buzzing along in the background. So the research is ongoing, and in many ways, it's being prompted or spurred along by the fact that we haven't found what dark matter is yet. And so, it could well be that one day the need for dark matter disappears altogether, and we find that one of these other theories works. So it's a really interesting question.
Or we go back to question one, where Kate said, what suspends the universe? Dark matter.
Yes, that's right.
Maybe. I don't know. Okay, Damien, thanks for your question. Fascinating. Let's move on to another question from Andrew in Melbourne. I like this one.
Hello, Fred and Andrew. Once again, Andrew Mitchell here from Melbourne in Victoria, Australia. Very interested in the last episode. Thought it was a great one. So many interesting topics and questions. Regarding the water on the moon, I was just wondering whether the analysis of that water actually tells us anything more about the water in the solar system and where the water from the moon, and hence the Earth, actually came from. Thanks. Bye.
Okay. That's an interesting question to throw up. We know now there's water on the moon. We've got brand new evidence of where it's at and how much there is, and I suppose the question of where it came from in comparison to the Earth and everywhere else it is in the solar system and the galaxy and the universe in general. And I'm of the belief that it is an abundant resource across the expanse of the universe. I think that will probably be the case, because if you take in the theory of, well, if we only find water on Earth, then chances are it may not exist anywhere else. But we don't find it just on Earth. It's on Mars. It's on the moon. It's in asteroids. It's everywhere. So, yeah.
It's even more than that, Andrew. Water is the most common two-element molecule in the universe, the entire universe, not just the solar system. Because we see it in gas clouds, we see it in, it sounds weird to talk about water in gas clouds, but it's vaporized water, but it is that H2O. And it is, of all the two-element molecules in the universe, it's the most common. The most common single-element molecule in the universe is molecular hydrogen, H2. So, there you are. So we shouldn't be surprised to find it everywhere. But the Andrew's point is well made, because what allows you to perhaps pinpoint where water has come from is something you and I have talked about before, Andrew, and at great length, which is the ratio of normal water to heavy water. Heavy water being the one with the isotope of hydrogen, which is called deuterium. So that ratio is really the fingerprint that we would use to discover where water has come from. And in fact, it gives you slightly contradictory results, because some of the comets that have been analysed for the isotope ratio of their water, some of them match the ratio of the water in the Earth's oceans, and some doesn't. So maybe some of the water in our oceans came from comets, but not all of it. As far as I know, the water on the moon has not yet been able, at least the water near the poles of the moon, which we talked about in that particular episode, I don't think it's been studied well enough, because we haven't got the ability to do it, in order to determine that isotope ratio. And I think that's one of the things that the Artemis astronauts will do when they get to the moon in maybe still 2024, we hope, to sample the water content of the rocks, of the soils of the moon, particularly in those regions where they never get sunlight. And then we can perhaps look at the analysis of the isotopes and work out whether that water is the same as the water on Earth, for example, that's the same isotope ratio. Something I think that is really interesting and something exciting to look forward to.
Oh, absolutely.
On Space Nuts.
Yes, indeed. I think it'll be fascinating, because the moon as an object has been hammered many times by lots and lots of things. So it's possible that the water on the moon got there after it detached from Earth and became our satellite. But I suppose it's also possible that whatever water was existent on Earth at the time of the event that created the moon meant it carried that water with it. It's it'll be interesting to find out which. Could be both.
Yes, it might be both. That's right.
All right, Andrew, great question. Thank you very much. Our final question comes from Steve, the bus driver. Now, this is the only question that Fred actually has been privy to in the whole program, but it's an interesting question, a little bit of a different spin on astronomy. It sort of really gets down to earth, quite literally. There he is.
Hi there, Fred. Hi, Andrew. My name's Steve. I'm a bus driver, and I have a question for you guys. When I drive the bus, I sometimes open the window, and at certain times of the day, sunlight strikes the edge of the window, causing a rainbow. And I know a little bit about it, but I would like to know more. I've sent some photographs to demonstrate what's happening, and just interested in a few things, like traditional rainbow is round and arced. Is that because of rain droplets? And the droplets are round, and in my case the rainbow is more or less a straight line. That's because the window's a straight line, and I understand it's reflection, refraction, dispersion. These things are going on. I'm interested to know more scientifically what's happening, and do the colours represent elements in the sun? The sun's elements, the hydrogen, nitrogen, whatever the sun's made up of. Maybe you could tell me a bit more about that. Thanks very much for your work. I'm a long-time listener, and look forward to hearing the answer.
Thank you very much, Steve. Steve, the bus driver. Okay. And I looked at the photos that he sent through, and quite spectacular colours that he gets through the edge of his window onto the dashboard or wherever. And they're pretty impressive. Indeed,
yeah, that's right. So what's happening there, Steve, is the edge of the glass is acting like a prism. It's just when you get sunlight in particular passing through a piece of glass that is not parallel as a window glass is, then yes, it's refracted and it is also dispersed. And dispersion is the process that produces the rainbow, which we technically call a spectrum. So what you're seeing is the spectrum of the sun. Now, you're quite right that it's by looking at such a spectrum that we can detect the elements in the sun's atmosphere. But you need a bit more than just the edge of window glass to do that. It needs a device called a spectroscope or a spectrograph, which can also use prisms, but it's the way that the light is manipulated inside that lets it identify the specific, small areas of the spectrum where the influence of those elements comes. And in fact, what they do is they make dark lines in the spectrum, which we call Fraunhofer lines, after Josef Fraunhofer, who was the German scientist who worked out what was going on. He was Bavarian. So the value about the elements in the sun, but they don't show up when you just bend the light through, through a piece of glass. In fact, a crystal sometimes does the same. Often, some people have a prism as well, which lets you see the beautiful colours. I think they're stunning.
Oh, they are.
What the colours that you can see, though, Steve, tell you is about the temperature of the sun. So the fact that you can see all the colours of the spectrum tell you it's a star that is emitting most of its energy in the visible region of the spectrum rather than out in the infrared and in the ultraviolet. And that's basically, we've evolved so that our eyes are most well matched to that part of the spectrum. But if our sun was a cool red star, then all the blue and green would disappear in that spectrum. You'd just have the red and the orange, probably red, orange and yellow in it. And likewise, if it was a very hot star, you just have the bluish colours in it rather than the whole spectrum. Just going to the earlier part of your question about why a rainbow is curved, it's a really interesting point, and it does relate to the fact that rain droplets are round, but that's not quite what it's all about. It's that you're looking at a very large number of them. So you've got these rain droplets which are in a whole area that the sun is shining on. And what you see then, the sun's behind you when you see a rainbow, you see this curved spectrum of light. And that's because each of those raindrops is actually taking the light, it refracts it and also reflects it. There's a reflection off the back of the raindrop, and that's why the sun's behind you, and it disperses it. So it disperses it into the spectrum. So altogether, bends the light through an angle of 138 degrees, which means it's coming back to you, because that's nearer to 180 degrees, which will be coming directly back to you. So it bends it through that angle, but it also disperses it. Now, that is being done by every single raindrop in the whole cloud of raindrops. And that's why you'd see a circle, because each one of them is bending the light through that same angle. And what it means is that the radius of a rainbow is 42 degrees. It's actually dictated by, that's 180 minus 38 degrees. So 42 degrees is the radius of a rainbow. And it comes about because everyone there's all these billions of raindrops, but they're all bending the sunlight through that same angle. And so get just a single bow of light. I'm not explaining it very well, but that's the reason behind it.
It makes perfect sense. Yeah, and
oh, good. Thank you, Andrew.
And they are rather fascinating. Yes, indeed. Thank you, Steve,
beautiful.
And stay safe on the road. That brings us to the end, Fred. We're done. Thanks to everybody who sent in questions, audio or text. And while I'm going through the thank you list, thank you to the audience, everybody who listens, the tens of you that listen to us. No, it's not quite 10. No, look, our numbers have been growing steadily during the year. I think at last report, our download numbers were somewhere in the vicinity of 60,000 a month. something like that, that's incredible, and it just keeps on growing. So thank you for spreading the word. Thank you for being a listener. Thank you for being a supporter of the podcast and for the kind words you send. I would also you in the studio for doing all the legwork to get it out there onto all those platforms, the Apple, the Googles, the Stitches, the myriad of podcast platforms that we are available on. And finally, Fred, thank you to you. Without you, it would be nothing. And I greatly appreciate the time you put into this. That's why we pay you the big bucks. And it's and it's just a joy to work with you, Fred. I really enjoy it.
Oh, that's good, Andrew. It's a pleasure to work with you too, and we go back a long way, as the audience probably recognises.
Yeah.
And it's always fascinating to talk about this stuff, and it's great to be able to share it with people.
Yeah, and
Thank you.
who knows?
Thank you for having me.
Oh, my great pleasure. And who knows what great revelations we'll be able to talk about next year. We will be back. I'm not sure exactly when, but we're going to take next week off. But we'll be back fairly early in the new year. So from us and our families to you, Merry Christmas, Happy New Year, and stay safe, and we will see you in 2021. Thanks for supporting the Space Nuts podcast, and bye for now.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.